One of my viewers on YouTube asked about building a circuit, a 555 timer circuit, that could generate a 60 hertz signal. And I told him I'd put together a video to show how this could be done. The first thing you want to do when you're doing something like this is just look at the spec sheet. And this is a spec sheet from TI, Texas Instruments. And this shows a very simple circuit called an astable multivibrator. This is astable operation. There's two primary ways you can operate the 555 timer. One is called monostable, and that means you need to trigger it to be able to get an output pulse. Astable means there is no stable mode. It continually generates an output. And the way it does this is by charging and discharging a capacitor. So there's a certain period of time that the circuit is high, and there's a certain period of time that the circuit is low, and you can adjust those settings. But this astable operation comes from a data sheet, and these data sheets have been out for at least 20 years, 20 or 30 years since the chip was developed. So when you go on websites and you see people showing a circuit that looks very similar to this, it may be missing a few components. Like right here, for instance, this is the different ways we can connect our loads, and you don't really have to worry about this for what we're doing right now. Our output is pin 3. You can hook an LED to it, a speaker. It can go into another piece of equipment. What the viewer on YouTube wanted was the ability to generate a false signal to an ECM to simulate a different speed for the car, because for modern cars the speed comes from a signal that's basically a waveform that changes frequency, and a change in frequency, a higher frequency means a higher speed, and a lower frequency means a lower speed. So he wants to simulate this. So here we have this block diagram that you see all over the place on websites, YouTube videos, and many of the people who use this never get around to telling you that this is right out of the spec sheet for the device. So when you want to use devices, the moral of the story is check and see what the manufacturer has produced, and chances are that'll save you a lot of trouble. So for this particular circuit here, we really only need two resistors. We need this resistor here, what they call RA, and we're going to make that a 1K resistor initially, and we're going to make this resistor down here a 15K, and we're going to make this capacitor a 4.7 microfarad, because these were some values that I had that'll work well for the frequency we're looking at. This capacitor is not really necessary, particularly if you use a CMOS version of the 555 timer chip. There's a bipolar transistor version, and there's a CMOS version. And I've never, in most of my applications anyway, I've never had to use this capacitor on the control. This is just to stabilize the voltage on pin 5, but if your circuit works without it, then it's fine. Don't include it. Pin 1 is our ground. Pin 8 is the power for the chip. Every chip, for the most part, needs power. Pin 4 is the reset pin, and it's what we call an active low triggered input, which means once you bring this low, the chip resets. And if you bring it to V+, everything's fine. You don't reset the chip, and the chip will actually work producing a high and low output. Pin 7 is our discharge, and this is actually the point in the circuit that is brought periodically to ground. So it allows the capacitor to discharge and also charge. When this pin 7 is grounded, the capacitor is discharging, and when pin 7 is open and not grounded, then the capacitor can charge. And this is how the chip works, just periodically charges and discharges the capacitor. So here's the spec sheet. We're going to build a circuit just like this. It'll only take a few minutes. So let's go ahead and get started. So here's my breadboard. I'm going to back up a little bit, and the first thing I'm going to do is put the chip down on the board. I like to put the chips on the breadboard with the pin 1 on the left downward side of the chip, so the lower left. And I like to put my power and we're going to use a 9-volt battery clip here. And I'm going to hook my ground to the blue bus on the bottom, and I'm going to hook my V plus to the red power bus on top of the circuit, on top of the breadboard. And what I usually do is use a hot glue gun and glue these down when I'm using my breadboards. A lot of times I don't want these to pop up. You know, you could take a circuit and put it on a breadboard and use it this way forever. You don't have to transfer it to a printed circuit board if you don't want to. And I use a lot of breadboards that way. So the next thing we're going to do here is, we know that according to our schematic here that our pin 8 goes to V plus. So we're going to hook that up. So we're going to take pin 8 and hook it to V plus. And once we've done that, we can cross that off our list. But what we'll do next, though, is hook pin 1 to ground. And that's why hooking up the breadboard this way works so well, too, particularly for a 555. 1's got to go to ground anyway, and 8's got to go to V plus, and the lineup is perfect for this. So far, what we've done is we have hooked pin 1 to ground, and we have hooked pin 8 to V plus. And this is a great way for you to do this, to keep track of what you're doing, is just to cross it off as you go. Alright, so now that we've done that, let's go back to the breadboard, and we're going to hook our resistor right here, our 1K resistor, between 7 and V plus. So let's go ahead and put that in here. This is our 1K. That's brown, black, red, if you can see that. And so we're going to hook that to pin 7, which is right next to pin 8 here. And then that's going to V plus. Okay, so that's done. We also need to hook RB, which is a 15K, between 7 and 6. So pin 7 and 6 have this 15K. So I'm going to go ahead and get these really close together here and go from pin 7 to 6. Alright, so let's go back to let's go ahead and zoom in here and show you this a little bit here. So we have 1 to ground, we have 7 to 6, we have the 1K from 7 to V plus, we have 8 to V plus, and one thing we didn't do yet was hook our pin 4 to V plus, because pin 4 is our reset, and that needs to go to V plus all the time unless you're going to be using the reset, which is usually not very often. So 4 is going to go to V plus here, and so we can now cross these things off of our list here. We've got 4 going to V plus through 8 here. We have 7 and 6 hooked together through our 15K resistor, and we have 7 going to V plus through our 1K resistor. Alright, and now we need to hook pin 2 to pin 6, and pin 2 is our trigger, and pin 6 is our threshold. So let's go back over here, and we're going to hook pin 2 to 6, okay, and as I said earlier, we're not going to hook anything to pin 5. When we get done with this, really the only pin we won't be using is pin 5 in this whole setup here. So let's go ahead and look at what we've got here so far. You can see we have pin 4 here going to V plus. We have pin 2 here going to pin 6. 8 to V plus. Here's our 7 to V plus. Our 7 to 6, and our 1 to ground down here. So for the most part, we're pretty much done here except for the capacitor. So the capacitor, according to our schematic here, not this capacitor, but the one we're going to use for timing, the 4.7 microfarad capacitor goes from pin 6 to ground. But it also goes from pin 2 to ground. So we've already made this connection here. So we're going to go ahead and hook the capacitor from pin 2 to ground, since 2 is right near ground anyway. So here I go and hook to pin 2, and this is a polarity. It's an electrolytic capacitor with a polarity on it. So this side has to go to negative. So we're going to hook that into ground, and we're going to hook this into pin 2. So we've got everything in place. So now we need to test it. So the way I'm going to test it is using a speaker. This is going to be a fairly low frequency. Let's see what we got. So I'm going to put one more wire in here on pin 3, which is our output, and I'm going to hook into this, and that's going to be our output, and then we're going to hook this to ground. And since we already have this wire for the capacitor going to ground, I'm going to hook to that, and we're going to hook this to a 9-volt battery, and you can hear it clicking, and this is a sign that we have a really low frequency here. Now we can check the frequency with a meter. If you've got a meter that does frequency, you can hook it up right now. But one thing I'm going to do, I know this frequency is really low right now, so what we're going to do is use a potentiometer, and I'm just using 2 leads in the potentiometer here, 2 terminals, the center terminal and one of the outside terminals. And I'm going to put that in parallel with this resistor, because this is going to have an effect on my frequency and allow me to adjust it. So there we go. I just hook that up, and I can adjust my frequency now, and I should have a pretty good square wave until I get to the real high frequencies, because once this resistance gets really low and it's comparable to the 1K we have here, then we start losing our duty cycle. Okay, so I'm going to check my frequency now. So instead of hooking up the speaker, I'm going to take my outputs going to the speaker and hook them up to my meter here. My meter does frequency, so I'm going to hook it up, and I've got my meter here set for hertz. It's kind of hard to get it on the screen here, but you can see my meter here has hertz right here, right there, and the meter is currently reading hertz. All right, so right now it's reading 48.8 hertz. I'm going to adjust it in to 60, or as close as I can get to 60. So I'm adjusting the potentiometer, I'm adjusting my frequency. Okay, there's 60 hertz, 60.1, close enough. And let's see what 60 hertz sounds like. I'm going to hook the speaker back up, and it should be a familiar hum. In fact, I think I had this set before to where it was already doing 60 hertz, so you've already heard it. But it's a familiar hum sound that comes from power. So this is 60 hertz. And I've got this hooked to a fairly large speaker so you can hear it. If the speaker's not large, you'll have a hard time hearing a low frequency like this. So that's it. We've built a circuit that produces a 60 hertz signal, and actually the signal can vary all the way down to about 30 hertz with these values, all the way up to 10,000 hertz actually. So that's it. Let me know if this was useful and if you've got any requests for other circuits to be built.